Hi boys and girls, this is lecture 7.6. The topic, area of a region between two curves, and this will be part 1 of our discussion. With a few modifications, you can extend the application of definite integrals from the area of a region under a curve to the area of a region between two curves. How do we find the area of a region between two function curves? Let's examine this diagram. This integral of f of x from a to b gives us the area of the region from the x-axis to the function curve f of x. This integral, g of x from a to b, gives us the area of the region from the x-axis to the function curve g of x. Notice that if we take this area and subtract off this area, the result is the area between the two curves. So we'll set up the integrals this way. The function curve f of x minus the function curve g of x integrated from a to b will give us the area of the region between the two function curves. The area of a region between two curves. If f and g are continuous functions on AB, and g of x is less than or equal to f of x for all x in the interval AB, then the area of the region bounded by the graphs of f and g and the vertical lines x equals a and x equals b is the integral from a to b of f of x minus g of x dx. Note, the function that is above the other must be listed first in the integrand. Okay, let's give this a try. Find the area of the region bounded by the graphs of y equals x squared plus 2, y equals negative x equals 0, and x equals 1. It's a good idea to sketch the region in question, primarily so you can see which function is above the other. Here's the function curve y equals x squared plus 2, and here's the function curve y equals negative x. We're interested in the area between the two curves from x equals 0 to x equals 1. So let's set up that integral. We're going to have the endpoints of integration from 0 to 1, the top function, which is x squared plus 2, minus the bottom function, which is negative x. And that will be integrated with respect to x. Let's simplify the integrand. This is going to be from 0 to 1, x squared plus x plus 2 dx. Now we integrate. That's going to be 1/3 x cubed plus 1/2 x squared plus 2x from 0 to 1. 1/3 times 1 cubed plus 1/2 times 1 squared plus 2 times 1 minus, and you can see that the second half is all zeros, 1/3 0 cubed plus 1/2 0 squared plus 2 times 0. This will be 1/3 plus 1/2 plus 2. If we get a common denominator, that's going to be 2/6 plus 3/6 plus 12/6, which results in an area of 17/6. Now let's find the area of a region between intersecting curves. A common problem involves the area of a region bounded by two intersecting graphs, where the values of a and b must be calculated. Let's take a look at our region. We can see that the function f of x equals 2 minus x squared is above the function g of x equals x, but we're not told the endpoints of integration. Since this is a bounded region, we need to algebraically determine where these two graphs are intersecting. We'll do that by setting the functions equal to each other. 2 minus x squared equals x. Since this is a quadratic, we'll move all the terms to the left side of the equation and set the right side equal to 0. This gives us negative x squared minus x plus 2 equals 0. Let's divide everything in the equation by negative 1. X squared plus x minus 2 equals 0. This quadratic factors into x plus 2, x minus 1, and setting each of those factors equal to 0 yields the 2 points of intersection, x equals negative 2 and x equals 1. So these graphs are intersecting at negative 2 and 1. That can be seen pretty clearly in this graph. However, that's not always the case. Be willing to go to algebra to determine where the two graphs are intersecting. Now we can set up our integral. We'll be integrating from -2 to 1, the top curve, which is 2 minus x squared, minus the bottom curve, x dx. The integral will be 2x minus 1/3 x cubed minus 1/2 x squared, and we're integrating from -2 to 1. This will give me 2 times 1 minus 1/3 times 1 cubed, which is just 1, minus 1/2 times 1, and subtracted from these quantities will be 2 times -2 minus 1/3 times -2 cubed minus 1/2 times -2 squared. This is 2 minus 1/3 minus 1/2 minus, here we'll have -4, and then a positive 8/3, and then a -2, which results in an area of 9/2. If two curves intersect at more than 2 points, then to find the area of the region between the curves, you must find all points of intersection and check to see which curve is above the other in each interval determined by these points. We're asked to find the area of the region between the graphs of f of x equals 3x cubed minus x squared minus 10x and g of x equals -x squared plus 2x. Here we have our cubic function f of x and our quadratic function g of x. Notice in the interval from -2 to 0, f of x is above g of x, but in the interval from 0 to 2, g of x is above f of x. Thus, we'll calculate this area using two integrals. In the first one, we'll list f of x first, and the second one will list g of x first. But first, we need to algebraically determine the points of intersection. That information won't always be easily obtainable from the graph. So let's set these two functions equal to each other. 3x cubed minus x squared minus 10x is equal to -x squared plus 2x. Moving everything to the left side of the equation, 3x cubed, the x squared terms cancel, minus 12x equals 0. When we factor out a 3x, we're left with difference of squares, x squared minus 4. This factors into x minus 2, x plus 2, giving us 3 points of intersection, 0, 2, and -2. This means in the first interval, we'll integrate from -2 to 0, f of x minus g of x dx, and in the second integral, we'll integrate from 0 to 2, g of x minus f of x. So that means from -2 to 0, we'll have 3x cubed minus x squared minus 10x minus a -x squared plus 2x dx plus from 0 to 2, -x squared plus 2x minus 3x cubed minus x squared minus 10x. Let's simplify our integrands. This is going to be 3x cubed, and then -x squared plus x squared cancels the x squared terms. -10x minus 2x gives us -12x dx. That's our first integrand, and we'll be integrating from -2 to 0. In the second integrand, from 0 to 2, we'll have -3x cubed, the -x squared plus x squared cancels again, and here we're going to have 2x minus a -10x, which is 12x. So this integrand will be -3x cubed plus 12x dx. The integrals will be then 3/4 x to the fourth minus 6x squared, integrated from -2 to 0, plus -3/4 x to the fourth plus 6x squared, integrated from 0 to 2. And the area of the combined regions is 24. If the graph of a function of y is a boundary of a region, it is often convenient to use representative rectangles that are horizontal and find the area by integrating with respect to y. In general, to determine the area between two curves, you can use the following guidelines. If your curves are in variable x, you'll integrate top curve minus bottom curve, and the endpoints of integration will be the left x value to the right x value. If your functions are in variable y, you're going to integrate right curve minus left curve, and your endpoints of integration will be from the lower y value to the upper y value. Find the area of the region between the graphs of x equals 3 minus y squared and x equals y plus 1. These are function curves in terms of y, and you can see from the sketch of the graph that 3 minus y squared is to the right of the function y plus 1. But we do need to analytically determine the points of intersection, so we'll set these two functions equal to each other. 3 minus y squared is equal to y plus 1. Subtracting over everything to the left will give us 2 minus y squared minus y equals 0. Arranging this in standard form, negative y squared minus y plus 2 equals 0. I'll divide everything by -1 and then factor. Y plus 2, y minus 1 equals 0. This means the y values of my points of intersection are -2 and 1. Therefore, we'll set up our integrand accordingly. From -2 to 1, the right function, which is 3 minus y squared, minus the left function, which is y plus 1. And in this integral, we'll be integrating with respect to y. Let's simplify our integrand. From -2 to 1, we have negative y squared, and then this will be minus y, and 3 minus 1 will be plus 2 dy. -1/3 y cubed minus 1/2 y squared plus 2y, and we'll be integrating from -2 to 1. This gives me -1/3 minus 1/2 plus 2 when you plug 1 in for y, minus -1/3 times -2 cubed minus 1/2 times -2 squared plus 2 times -2 equals 9/2. That's it for today's lecture. Here we have another applied area problem provided by Foxtrot. Pizza. God bless you, boys and girls.